see this. I hope you will see my lecture slide, right? Okay, so let's continue. In lecture 1, I hope all of you know the answer to this question of what is a robot, and also know this answer to this question of what can be done with the use of a robot, because I give you a short history of inventing robot in China, in Western country, and in Japan. And I ask you to do a comparison between human being and the robot, all right? And most importantly, you know that actually the first generation of robot was made in China in the form of puppet, shadow puppet, etc. And also, you know that we can deploy robot in industry, in hospital, and in service sector, etc. All right. So by now, you should be convinced about the importance for us to invent a robot, right? Because of many exciting applications which could be performed by today's robot. Then you may want to know, okay, how to achieve the design or invention of the robot. So it is very important for you to adopt the system viewpoint. Consider a robot is a system, and in particular, at the entry level, you should consider robot is a motion system. Subsequently, you can consider robot is a control system, robot is an information system, robot is a communication system, robot is an intelligence system, etc. So at the bottom, okay, at the foundation level, just think about the motion system inside robot, all right? That should be good enough already. Okay, why a robot is a motion system? So this slide gives you the blueprint of a robot, which will help you to understand, okay, the key step which involve in the transformation from a task to motion in task space, then motion in joint space, then motion under control, then the motion as an output from the body of the robot. So you see this motion flow. So let's give you a very convincing answer about this viewpoint of thinking robot as a motion system, because we need to know how to transform a task into motion in task space, the motion in task space into motion in joint space, how to make a motion in joint space to be controllable, how to perform or control the motion so that the body of a robot could output the motion. All right, keep this in mind, then it's easier for you to study robotics. All right, so and here you see the there's a box with keyword robot intelligence. All right, that indicate to you what should be the future development in robotics. The future development in robotics is to make a robot to have a human-like mind. This is because for us, okay, we can autonomously plan our motion, make a decision, okay, etc., etc. The reason is because we have a mind, human mind, all right? Then what should be the robot mind, all right? So that is a very important aspect. And this course will link you to the study of AI, artificial intelligence. And you see the connection between artificial intelligence and robotics, all right? So this slide also help you to venture in future into the study of AI, all right? So it's quite important. Okay, then in the first lecture, I already answered this question. In order to become an expert engineer in robotics, what should be the basic knowledge and the skill for you to have, all right? So basically, you need to know the knowledge which are related to these 4 modules, all right? Module number 1, how to design the body of the robot. Module number 2, how to design the mind of the robot, okay? And module number 3, how to analyze the motion relationship inside the robot. And the module number 4, how to make a robot to perform controllable motion, all right? So these are the basic knowledge for you to have in order to become an expert engineer in robotics, all right? So once you have all this knowledge, the skill you need to have is to know how to design, apply the physical principle into the design of any intelligent product such as a robot, right? And this also very important for you to adopt customer or user-centric mindset or thinking. So when you want to come out a new robot, think about the user first, okay? Who will be the user of your robot? What are the need from this user, all right? So the first 2 questions basically is for you to know this, okay? Product specification basically means the need from the user, okay? Why the user will buy your robot, all right? So after that, for each need, what should be the solution? For each solution, what should be the condition, parameter, performance, specification, etc. That should be the design specification, all right? So once you know the user, you know the need, you know the solution, then you can combine all the possible solutions together to come out the conceptual design. You may have many conceptual design. Among all the conceptual design, you choose the best one, all right? Then subsequently, then you implement, okay, the best design, okay? Then build up the prototype to do the testing, then improve it, etc. Right? So that should be the skill. This skill is generic, okay, for the design of any intelligent machine, but it's not unique to robotics. So you just borrow this skill, okay, to guide you to apply, learn the knowledge, okay, in order to achieve the design or invention of your robot. So these knowledge are quite specific in robotics, but these skills are generic, okay, in general. So for those of you, if you study in mechanical engineering, then this is very, very important to you, right? But for those of you, if you are not, okay, in mechanical engineering, for example, you are in the computing engineering, this slide is also important for you, because when we talk about the product may refer to hardware, may also refer to software. If you come out to do programming, it's good to have this mindset. It's very important, okay? Treat the software as a product, okay? Then you will come out a better result, all right? Okay, then for this lecture, so basically I help you to adopt the viewpoint of the system. In this way, you think robot as a motion system. Then in this way, immediately it's easier for you to understand what should be the key element or key subsystem inside a robot, right? So let's start with the concept of a system, right? So you may want to know, okay, what is a system? Okay, so actually by definition is very simple. Okay, a car is a system, a building is a system, and your handphone is a system. So a system means inside you have a many entity, many element, or many module or key component. They interact together, okay, for the same objective of achieving the output intended by the system. All right, it's like a car. You have an engine, you have a wheel, all right, then you have a fuel supply system, power supply system, etc., and the sensor system, right? Then plus a steering wheel, transmission system, and all these systems inside the car work together in order to make the car to be able to move from one location to another location. All right. So then it's easier for you to understand this definition. So you have a different kinds of element which interconnect together, okay, for the purpose of achieving the intended output from the system. All right. And how to understand a larger system is on Earth, a larger system in the solar system, in the larger system in our whole universe. Then you see the advice from Nikola Tesla. Just think about the three sensors, all right? Energy, frequency, vibration. Then you will understand the secret of the entire universe. Just think about it, all right? So if you follow my keynote speech from the YouTube, you can find my keynote speech. I also just extend this statement. So this is to understand the secret of the universe, because every system is animated by energy. All right. So then energy basically is a vibration. What is energy? The molecule vibrate. All right. Then when there's a vibration means what? Periodic motion. Once you have a periodic motion, we talk about the what? Amplitude, frequency. Now you understand energy, frequency, vibration are basically the secret behind any system in the universe. All right. Then how to understand the meaning of a system? My advice is what? Three keywords: space, vector, time. Because we have a knowledge space, a knowledge vector. Then the knowledge vector and the space vector evolve in time. All right. So actually, to understand the entire world is not so difficult. Just stick to some simple keyword. It's very important. All right. Now, let's say I give you this robot, ask you to name 5 systems, okay, from this picture. So I guess it'll be easier, all right? A robot must have a vision system to see. A robot must have a speech system like us to talk. A robot must have a ear like an auditory system. A robot must have an arm, like manipulation system, grasping system, locomotion system, control system, communication system, programming system. Actually, you can name more than 5, all right? Quite straightforward. But this slide help you to think in terms of a system, right? But what is a system in terms of signal flow and the knowledge flow or motion flow, right? Then in this case, you must think these 3 key elements. One is about the input, second one is about the output, third one is about the relationship between input, output, and this relationship in frequency domain, we call it as a transfer function. In time domain, we just call it as a relationship function, right? But for those of you, if you did the study of a control theory, then you know this terminology, like transfer function, basically is an equation in frequency domain, right? So then this slide help you to understand, okay, the relationship, okay, between input and the output, and inside the system we have this relationship function or transfer function in frequency domain. All right, and this is an open loop because there's no feedback from the output back to the input, and later on you will see that actually it is very interesting for you to know that in the whole universe, all right, all the systems more or less are being designed with the use of a feedback control loop. It's like a human being. Actually, our control system is a feedback control system, all right? So we have a sensor. Sensor provides a sensory feedback to the input. Then we can compare the desired output with the measured output. Then we get the error. We use error to make a decision about the next action to take. So that is the beauty of a feedback control system. For those of you, if you did not study control theory, actually it's not complicated at all, all right? From here you will see, so this is the actual output. Response means what? Actual output. Input means what? It's a desired output. It's like I want to set the room temperature to be 25 degrees. 25 degrees here. Then we use a sensor to measure what is the actual room temperature, maybe 20 degrees. Then there's a difference of 5 degrees. That is the error. Then we use the error to make a decision about whether I want to increase the temperature or reduce the temperature until the error becomes 0. That is the beauty of this design. All right. Conceptually, I guess a primary school student could understand this one. Okay. As long as this one is 0, no action. If it's not 0, then we take action until this becomes 0. So that is the beauty of negative feedback. Why negative feedback? Because this is the error. Error means what? Difference between desired output and the actual output. When you compute the difference, means what? One must be positive, another must be negative. Otherwise, it's addition. Addition is not difference, John. Only subtraction between two numbers, then get the difference. Difference means what? Error. All right? Then feedback control system add on error. It's very simple. Okay? But complexity come from the way how to make this error to become 0. Then we have a different solution. That is only complexity. All right. Philosophically, primary school student should be able to understand this one. But with this understanding, eventually, this slide may motivate all of you to study control theory. I believe control theory has a tremendous importance, not only for natural science, but also for social science, right? So this is a very, very important philosophy, okay? So for those of you, if you have a chance to study control theory, you must do it, right? It's very, very important, okay? So then look at the output. It is very interesting for you to know that all the output divided into 2 categories, transient response, steady state response. Okay, later on you will know. If let's say I want the room temperature to be, let's say 25 degrees. If instantly we reach 25 degrees, that means this system has only steady state response. That means 25 degrees. This is a steady state response. But in practice, the air conditioner system will take time to, let's say, let the room temperature to increase from 20 to 21, 21, 22, 23, 24, 25. All right. Sometimes it may overshoot 26, 27, then come back 26, then 25. All right. So these kinds of oscillation means a transient response. Right. It's quite simple. But graphically, you will see. Okay. If let's say we want the room temperature or want the motion to rotate 10 degrees, if instantly we reach 10 degrees, that is a steady state response. But when we rotate due to inertia, then overshoot and oscillate, that is a transient response. So transient response will converge to steady state response, right? So then how to judge, because of a transient response, then we want to know, okay, how good is the response, how bad is the response? Because steady state response is always good. That means there's a 0 degree, 10 degree, 10 degrees intended, then there's no judgment at all. It's only when there's a transient response, then we still have an error. Then we need to know whether this system is stable, how long it takes for the transient response to reach steady state response, all right? Whether the transient response will reach the steady state response or not, all right? So this is 3 criteria: stability, response time, response accuracy, okay? It is also very interesting, important for you to know this very, very simple conclusion, because I guess in the textbook of control theory, they never mention this, and a lot of people overlook this. But once you know this answer, you will be excited for you to live in the world. What should be the best system in the universe? Answer this question. All right. If you start to think about this question, if you know the answer, then you will enjoy your life on Earth. The answer is what? The best system in the universe are static system. Static system means what? The system has an absolute stability, 0 response time, 100% accuracy. You see, based on these three criteria, stability, absolute, 100% stable. Response time, 0, all right? Response time accuracy, 100%, all right? So why static systems are the best system in the world? You just imagine if, let's say, we have a flying robot, in future, we can consider airplane as a flying robot. If, let's say, you want to fly from Beijing to Paris, if you can achieve the result of making flying robot to be static system, it means what? The traveling time from Beijing to Paris is 0 seconds. That means the captain, the pilot, turn on the engine of the flying robot. Instantly, you reach the airport in Paris. All right, let's save your time, John. That is interesting. Understand? So best system in the universe are static system. But the bad news is what? Most systems in the universe are dynamic system with a transient response. Right? For those of you, if you are interested in religion, right? So you see, this is an instant technology. This is a former president of Taiwan University. All right. So in which place we could find that the most systems are static system or the best system? The answer is what? Is heaven. For those of you, if you like to study religion, you can link, okay, your study with this slide. It's very interesting. All right. Okay. So then this slide showing you what is stability. If let's say your output transient response go to infinity, never come back to steady state response, then the system is like a bomb. It's not stable, right? And so that is about the stability. Response time, you see, start from here all the way until the output reach the steady state response. So it takes a little bit of time now, okay? For many real systems, it's difficult to achieve a 0 response time, all right? So we can make a response time as short as possible, all right? Then response accuracy, for example, we want the output to be here, like, I don't know, maybe 0.5, but actual output could be 0.6. Then there's an error of 0.1, all right? So, and hopefully we want the accuracy to be 100%. But today, for most systems to achieve 100% accuracy is not a problem. We can achieve 100% accuracy or 100% stability, but not 0 response time. So you see the challenge in the design or control of the robot is to make a response time to be 0, right? So if we can achieve 0 response, it's very interesting, John. Okay, so it means what? You can travel from Beijing to Paris within 0 seconds. Then it's a magic, John. If you are able to design such a flying robot, then go ahead to do it, all right? Okay, so then we apply this concept to the situation of the robot. So robot is a system which more or less imitate human-like skill, human-like intelligence, right? And let's say we want to design robot for undertaking welding tasks. Then from this slide, you see a robot has an arm, has a tool, has a brain. A brain is here. You have a control box that has a display, etc. Okay, and also has a workspace, etc. So that gives you an idea about the system. So you have all the elements. Okay, and let's say for material handling task, so you have a robot. You see robotic arm. You have a brain, and you have a tool. All right. So you have a display, you have a computer, you have a brain channel, right? So give you an idea about the system. Then this is for the pick and place palletizing. So you have a conveyor. Again, you see you have the robot has a body, has a brain, and has a mind, a software system inside, etc. And then in this case, it's more complex workstation, which involves the use of a 2 robotic arm. And in this case, the robot has an eye, John. You see 3 cameras. These are the 3 eyes of the robot, right? Then robot has a brain, has a body, has an eye, etc. Right? So it's quite straightforward. Okay. So it's like any system, a robot system must have an input. Then what is particular? Okay, with the robot's input, the answer is the input to robot should be task or description of the task. Right? If today's robot cannot directly take a task as an input, then human must be there to help the robot to transform a task into description of the motion or equation of the motion. All right. So then equation of the motion will be the input of the robot. Then what will be the output? Okay, at the lowest level, the robot must be able to output motion. If the motion are related to the intended action, then that will give you the appearance that the robot is performing action. If the output action corresponds to the intended task, then the output from the robot gives you impression that the robot performs a task. All right. So then from this slide, more or less you see the input output from the robot. All right. So then once we identify all these subsystems, okay, inside the robot, then we want to know what should be the key system or most important one, all right, inside a robot, okay, because all these systems must work together in order to transform the input to the output. All right, because for a robot, it's not just so simple, just write a single equation, a single relationship equation to transform an input to output. It's not that simple, okay? Then that is a mathematical game, because once you build such a complex machine, all right? So you will see inside a robot system, there are many subsystems, they work together in order to transform an input to the output, all right? Then what should be these important subsystems, all right? First, the robot must have a body, Then what is the important subsystem inside the body? Answer is what? Mechanic system, all right? And the robot must be able to perform a controlled motion. You remember the module 4, control the motion. Then it is very important for robot to have a control system, all right? And a robot, you see the module number 2, a robot must take input, okay? Then transform the input into the output. How to understand the input? So that is a module number 2, all right? Inside the blueprint of a robot. So it will take a description of the task, okay, all the way into equation of the motion. That is a programming system. So with the use of a programming system, then user can help a robot to do such a transformation, all right? Then on top of that, if let's say we want to make a robot to have a human-like behavior, etc., then we need to have a vision system, because human being has an eye, human being has a mouth, has an ear, right? And we can use our voice to communicate. But actually, robot can use a network to communicate. Then from the presence of a communication system, immediately you understand robot is a mini version of IoT, Internet of Things. All right. So then you see you can connect the topics about the robotics with the topics about the IoT already. All right. So you see, by doing the study of this course within such a short period of time, actually you more or less you fully understand what is robot, what is automation, what is IoT already. Okay, so of course you remember Tesla's recommendation. Okay, energy, frequency, vibration. Any system must have energy, right? Because without the use of energy, then there's no signal. Without the use of energy, there's no motion, all right? So power supply is very important, okay? So that gives you an overview about that, okay? How to design a robot's body in order to transform an input into the output. And the most importantly, the number one output should be motion. Now you understand robot is a motion system, because number one output from a robot should be motion, because without the motion, then your robot more or less not much useful, all right, in industry, all right. Of course, for some application, you just have a robot just talk, okay, without doing anything. But application will have a tremendous limitation, all right. So in industry, number one output from robot should be motion, very important, all right. So then immediately understand the first three systems are most important in robotics, all right. So mechanic system is extremely important, all right. Then how to design mechanic system? Actually, it's very simple. So inside the robot, we only have two basic building block for mechanic body. One is called as a link, another is called as a joint. So you have a link, you have a joint, then you put them together, then you form a robotic arm or a body of any kinds of a robot. So it's quite simple. Just link and the joint. Link is just a rigid body with a certain geometry, and inside the link we can house other component. All right. Joint means is a device with a two rigid body, and these two rigid body can undergo relative motion. All right. So that output motion. So joint is a location at which robot should be able to take input motion or produce output motion. All right, that is a motion device, because inside the joint we can achieve a relative motion between a pair of rigid link. All right, okay. So then this video basically will help you to understand what is a joint. Then when the joint drives the link, then you see all kinds of motion, right? Sorry. So this is one joint. Axis means a joint, okay? Axis here means rotation axis of the joint. Then second rotation axis of a joint, third rotation axis of a joint, and because once you have a rotation axis, then you get output rotational motion. Fourth axis of a joint, then fifth axis of a joint, then last one is a sixth axis of a joint. Okay, rotate like this. Then based on this slide, you understand your own arm. You can try to play with your arm. Your own arm looks like this robotic arm. All right? Okay? Now you see each axis is under control of actuator. Motor means actuator. Then we must have a brain. Brain allow us to do programming. All right? So we can help the robot to program the motion, okay? And at the last link of the robot arm, we can attach all the tools, okay? Eventually we can attach the hand. Right? So this video basically gives you a very good summary about the industrial robot. If you understand this video, actually you understand robotics already. All right. So it's not very complicated, but however, once we zoom into the detail, you need to have a lot of knowledge already. Okay, so this video gives you a very good summary about what is robot, and then I use few slides to help you to understand. All right, so and graphically to represent all these axes of a rotation, so we use a cylinder. All right, and we may also have an axis which could undergo linear motion. Okay, so but in this case, all the axes only produce rotational motion. All right, so this is the graphic representation. All right, then for this type of a robot, you will see there's a one axis which can undergo linear motion. We call it as a prismatic joint or prismatic link. Right, so you can count how many degrees of freedom. So you see This is the one axis of rotation, second axis of rotation. This is the axis of translation, then axis of rotation. So you have a 1, 2, 3, 4, 4 degree of freedom or 4 axes. One axis is for linear motion or translational motion, right? Quite straightforward. Okay, so that is the first important subsystem inside a robot. The second important subsystem inside the robot should be control system, all right? Because the joint must be driven by actuator. It's only the actuator will power joint to inject mechanical energy, because without the mechanical energy, there is no motion. How to convert electric energy into output of a mechanical energy? This device is called as a motor. When we put the servo motor, means a motor under control. It's called as a servo motor, okay? Motor under control, all right? And the control is a feedback control. And all the motion must be synchronized together, all right? Then we must use a controller to coordinate the synchronization, coordinate the motion. Actually, this slide already give you a good introduction about the IoT, Internet of a Sensor. Do you see the internet is a network, all right? Do you see the sense? Sense here is two major sense are motor, sensor, all right? Servo means under control. Under control means what? You must have feedback control loop. Inside feedback control loop, you must have a sensor, all right? So all this motion, actually there's a sensor there. So this gives you a very good introduction about what is IoT. This is a mini version of IoT in which you see the network, you see the controller, you see the sensor, you see actuator, right? So when you study the third topics, actually it will complement your understanding about the robotics, all right? So these three topics are strongly interrelated, all right? So this is it's a perfect combination in this course to combine robotic, automation, IoT together, all right? So within a single course, because they are interrelated, you actually been exposed to three important courses, okay? Robotics, automation, and the IoT, all right? So, and then for programming, because today, the majority industrial robots are not so smart, okay? They do not have a human-like mind. Therefore, human being must be there to help robot to do the planning, okay? To do the motion planning. So after planning, we can eventually to simulate the motion in the virtual environment, all right? And today, some of you may heard of this terminology, digital twin. So actually, these are the digital twin of a production arm, digital twin of a robotic arm, digital twin of a humanoid robot, or digital twin of a human operator already. So from this video, you already have an idea about the digital twin. But this video was made by our student 20 years ago, right? So it's around the year 2000 at that time, okay? Okay, so that gives you an idea about the intervention from a human being in helping robot to do programming, right? Then visualize program the motion to be performed by robot, etc. Right? So the previous slide gives you a good introduction about the robot's motion system. So you see a robot is a system which has an input, which is an output. Number one, output should be motion, all right? And how to achieve a transformation from input to output. A robot must have a mechanic system, control system, programming system. These are the three basic subsystems inside the robot. On top of that, we may have a vision system, speech system, communication system, power system, etc. All right. So then next question is, a robot is not a static system. You remember at the beginning of the introduction, we remember my conclusion that best system in the universe are static system. Okay, that is a good news for you to know. Okay, where to look for the best system. But bad news to you is what? Most systems in the universe are dynamic systems, including robot. All right. So once you face dynamic system, then you want to know how good are your dynamic system. This is why we need to look at the performance evaluation. How good are the dynamic system of the robot? Now you remember we have 3 criteria for us to make a judgment. One is about the stability. Second one is about the response time. Third one is about the response accuracy. All right. It's very simple, John. All right. So keep this in mind. Then we apply the same 3 criteria to judge robots' performance. Stability is easier because once you come out the design of the robot, your robot must be stable. Otherwise, your robot become crazy. All right. We have a crazy human being, but we should not make or produce or invent crazy robot because crazy robot is useless, John. Right. Then after that, then we must make sure the response time is very short. All right. Now you see this one. So you see, today we can achieve 100% accuracy. It is not possible for us to achieve 0 response time. All right, just keep this in mind. Then our effort is to make the response time as short as possible. You see, just now, this robot move very fast, okay? So it means what? Response time is very short, but not 0, okay? Then stability is easier for you to understand, but for industrial robot, normally we do not have such a concern. Such concern only come from the study of a humanoid robot, because when we undertake a biped walking or when humanoid robot undertake biped walking, due to gravitational force, then there's an issue of stability, right? So it's quite straightforward. And then this video showing you that it is not an easy task to achieve stability by robot, by humanoid robot, but not industrial robot.
Schwarz Human, in Blau das Now-Team HTWK. Human kommt aus Bremen, HTWK aus Leipzig und beide haben eine Neuigkeit von diesem Jahr umgesetzt. Eigene Trikots. Anstoß hat anscheinend Human. Und neu dieses Jahr ist auch die Detektion des Handgriffes. Das bringt ein paar Sekunden, in denen man reagieren kann oder reagieren kann, sollte es das andere Team nicht erkennen. Und das sieht gut aus. Beide Teams haben es erkannt. Zweikampf jetzt in der Mitte.
So there's an international competition called Robotics, right? And there are many universities involved. I guess some universities from China have also participated in such an annual event. So this is a very good learning platform for students and also very good learning platform for researchers, all right, to improve the design skill, control skill, and the programming skill for humanoid robot. Then from this video, immediately you see biped walking has a big concern about the stability, right? So then this is just a small exercise. I guess you should be able to do it. So I consider this as the homework assignment. So you do it at the home because the answer is given to you. But if you have some issue, then you just let me know. We can discuss. So I treat this as a home assignment in order to save time because we may run out of time already. All right. So, but then for mobile vehicle, also there's a concern of stability when the vehicle move along the circular path. Because when you move along the circular path, then there's a presence of a centrifugal force. For biped walking, there's a gravitational force, which will cause instability. For when you have a mobile robot or high-speed mobile robot. And when the mobile robot move along the circular path, then there's a centrifugal force. Centrifugal force is parallel to the horizontal plane. This will make robot, okay, to turn over, okay, about the horizontal axis, all right? So that may cause instability, right? So this is just small exercise for you to understand this issue, okay? And then for industrial robot, normally there's no issue of stability, but response time, okay? So here is one more example for you to see response time. Okay, so then another issue is about the response accuracy, but this one is also a small exercise. I just roughly go through, and this also is related to the next lecture about the motion planning equation of trajectory, right? For example, we have this prismatic joint. Prismatic joint will drive a link to undergo linear motion, all right? So then this joint can produce a maximum acceleration plus minus 5 meters per second square, right? And we want to know how to make this slider, okay, to travel for 20 centimeters within the shortest time, all right? So then based on the question, you come out with some key information. Let's say we assign the coordinate system in this way. Then initially the robot is at the 0 position along the z-axis. Then the destination is when z equal to 20 centimeter, right? Maximum acceleration, deceleration is 5 centimeter per second square, right? And then now we want to know what is traveling time, okay? So here we just make this robot to make 2 movement. But next lecture, we are talking about the trajectory. That means 2 equations of a trajectory. One is to speed up from 0 second to half of the traveling time. Second movement is to slow down from the half traveling time all the way to the entire traveling time. So basically just 2 time interval, okay? And the entire time traveling time is t, then half should be t divided by 2, okay? Then during the speed up phase, right? Because the acceleration is a constant, then you can apply your knowledge learned in physics in year 1, right? Displacement is proportional to constant acceleration times traveling time square. So it's 1/2 AT square. I guess you should remember this equation. I believe this is a high school equation, okay? So then when acceleration is constant, then velocity is equal to initial velocity plus increment due to acceleration, so a times t, right? Because initial velocity is 0, then have these 2 equations, so it's quite straightforward. Then during the slowdown phase is a deceleration. Then displacement is equal to the displacement due to initial velocity. Because here you see we do not put the initial velocity here because the initial velocity is 0. Then travel distance due to initial velocity is 0. It's 0 plus this one, okay? But once you slow down, because at this point you have an initial velocity, initial velocity times duration of travel. And this is a deceleration, okay? Then should be negative a plus negative a plus negative is negative, okay? This is a constant. Then this is it's like a 1/2 AT square. T, because this is counted from this point of time. So this is a time duration. Because t minus t/2 is the duration of a travel for this slowdown motion, all right? So this equation is the same as this one, all right? So it's only the boundary conditions are different, all right? Then, because when the t equal to, because you use this equation, when t equal to capital T divided by 2, that should be the location initial location for the second motion. Initial location for the second motion, we can calculate equal to this one. So it's quite straightforward, right? And then what will be the initial velocity for the second motion? Because when t at this point of time, so you just apply this equation, you will get the v capital T divided by 2. Okay, so I guess you can easily work out and verify this result. Okay, now you can put together, okay, because you substitute this one by this one, substitute this one by this result, then you rewrite this equation in this form. From here, then you see you only have a single t here. It is the time, all right? And now we know when t equal to capital T, the travel distance is what? 20 centimeter, right? So immediately you substitute this small t by capital T. Then this result should be equal to 20 centimeter, which we use a meter. 20 centimeter is equal to 0.2. Okay, then you see from this equation, we only have a single capital T. You can easily solve it, right? Immediately you get the answer. So that is a traveling time. Okay, so it's quite straightforward. So I help you to slightly go through all this solution, and I consider this is like a homework. Okay, so you must do it. Okay, you can work together as a group to verify this solution is correct or not. Okay, try to do it. Treat it as an assignment of a homework. All right. Okay, so then in this way, you know solution. Then response accuracy is also a quite important concept. But good news is today we can achieve 100% accuracy. So it's not the issue. But for response time, difficult to achieve 0%. Okay, so I use this example for you to understand why there's a concern about the accuracy. If let's say your control has an error, that the error of an angle will produce an error of a position. For example, this is a robot. Normally the tool is attached at the joint 4. If we just look at the top view, that means the view inside the XY plane, then we just focus on the Y coordinate and the X coordinate to see whether the error of the angular motion at each joint will produce error in the XY coordinate of the tool or not, because our tool or hand is here, right? So then we just draw this top view. Okay, for top view, only the first 2 links will play a role. We have a link 1, link 2. This is a joint 1, joint 2, right? And then you will undergo motion, because joint 1 will rotate theta 1, joint 2 will rotate theta 2. But pay attention, because the motion is relative motion. So the link 1 will rotate about the base link or the ground. And link 2 will rotate with respect to link 1. So that means theta 2 is the angle between link 1 and the link 2, because link 2 rotate on top of a link 1, all right? Keep this in mind, it's relative motion, all right? So when theta 1 has an error, theta 2 have an error, then obviously your Y coordinate, X coordinate will have an error, all right? So I help you to write down the equation. Once you have this relative motion theta 2, you may want to know what is the absolute orientation of a link 2 with respect to this global coordinate system. So you see theta 1 plus theta 2 actually is the orientation of a link 2 with respect to this OXY plane, right? Okay, so, okay. Then you can write down the equation. What will be the Y coordinate here? Y coordinate come from a contribution of a link L1. So you just apply cosine function of L1 times cosine theta 1, give you the displacement along the Y-axis due to link 1. Then for link 2, we will contribute also to Y coordinate. So displacement along Y coordinate is equal to L2 times cosine theta 1 plus theta 2, right? So this is a solution. Actually, this already help you to understand module 3 in robotics. That means the relationship about the motion, all right? So from here, you see relationship between theta 1, theta 2 are considered as an input motion. Okay, so input to the mechanical system. And Y is considered output motion, coordinate or displacement, right? So this is already kinematics or relationship among the motion inside the robot, all right? So you see, module 3 more or less is present here, all right? Then we can compute velocity, right? So we just calculate first order derivatives of y with respect to time. Then I guess this is just a simple mathematics. Then this is the velocity of axis 1, velocity of rotational axis 1, velocity of rotational axis 2, right? If let's say we have an error, then we can convert this derivatives equation into variation equation. That means we take out the dt, then small d replaced by variation. Variation of a y is proportional to variation of theta 1 and also proportional to variation of theta 2. So this is a very useful equation for us to evaluate the error or accuracy. If let's say we have error, maximum error for theta 1 is 0.01, maximum error for theta 2 is 0.02. Then 0.01 plus 0.02, A together is 0.03. Then you put in the number, then you can determine the error at the 2, all right, at the end of your robotic arm. So I consider this also is a home assignment, so you must do it, okay, verify whether you get the same result or not, okay. So by now, you know, a robot is a motion system and it's a dynamic motion system. It is not a static motion system. The best system in the universe is a static system, all right? And our effort is to transform a dynamic system to behave like a static system as much as we can. Therefore, we need to make the system, dynamic system, to be stable, to be fast enough, to be accurate enough, all right? Then next question is how to design a motion system for robot. So this is just some design consideration, right? So it's like what I say, when you design a robot for a user, you must know who are the user, what are the needs of this user, then what should be the functionality of the robot that you are going to offer to your user, okay? Then for each functionality, what should be the solution, okay? Then among all the possible solutions, then you can come out the conceptual design solution. Among the conceptual design solution, you choose the best one. Then once you choose the best one, then you just implement the best design solution or conceptual solution, all right? So then when you design a robot's mechanic system, just now I already tell you, there are 3 very, very important subsystems inside a robot. First is mechanic system, second one is control system, third one is a programming system, all right? Then for the design of a mechanic system, what should be the major concern? Actually, there are 3. Number 1, how to design appearance. For industrial robot, appearance is not important, but for humanoid robot, service robot, appearance is very important. Second one is the design of a mechanism. Third one is design of a structure, all right? The last 2 are important to all kinds of a robot, all right? Then for control system, because all the control system will make use of a feedback control loop. So you remember at the beginning, I asked you to understand this feedback control loop because conceptually primary school student could understand also, okay? So you have a sensor to measure actual output, you have a desired output, you compute the difference is the error, right? That is a feedback control loop. Inside the feedback control loop, there are only 3 important modules. One is input, is a sensory device. Second one is actuator, which will produce the output. And the third one is a controller, which will make a decision based on the use of error. You remember, when error is not 0, take action until the error becomes 0, right? So there are 3 basic building blocks inside control system, okay? The input sensory device, output actuation device, and the controller, which make a decision, all right? So this, but in general, for any control system, you must consider what are all the possible input, because the input may also refer to the keyboard. Keyboard can capture humans' intention, right? And the output could be the screen. We may want to display some information on the screen. So it must generalize the input, output, and control. Okay, don't restrict to the sensor, actuator, right? Okay, so these are the key consideration. But when you design programming system, right? So, but in the topics of IoT, I will cover a little bit about the digital microcontroller. Then on top of that, we need to have an operating system to have a, it's like a user computer interface. Okay, so inside the user computer interface, typical example is operating system. Like every one of you know what is Windows 11, Windows 10. So all these are operating system, right? And then second, the important component should be programming language. I believe some of you may have heard of Python, C, C++, MATLAB, etc. All these are the programming language, right? And then lastly, for your own application, it's always good to have an operating system like a user interface. So you see, we have a graphic operating system like Windows. Actually, there's a user interface there. But once you pop up another application, each application may have its own graphic user interface. All right, so these are the knowledge for you to know. Okay, so that's all about this second lecture. Okay, so in the second lecture, you understand a robot is a system. What is the best system in the universe? What is the control, feedback control loop? Okay, inside the system. All right, and inside the robot, a robot is a system, and the robot will take task description or motion description as an input, produce a motion action task as an output, and the number one output from a robot system should be motion, right? And then how to make a robot to perform the motion, how to enable a robot to perform the motion. We must have an inner subsystem inside the robot. And there are three most important inner subsystems inside the robot. Number one is a mechanic system. Number two, control system. Number three, programming system. All right. So that gives you idea about the system. All right, robot system. All right. So at least from this lecture, you understand input, output. Right. The next question you can keep in mind is how to transform an input into output. And since we do not have time to cover the whole answer, I just tell you the last part of this transformation in next lecture. So next lecture, we'll focus on this question, how to transform input to output. Because here we know we are able to, what should be the key consideration for us to design a mechanic system, control system, programming system, then we can build up the system, all right? Once we build up this motion system, and we understand what is input, what is output. Next question is how to transform input to the output, right? So I just, in the next lecture, I just give you an important answer, right? So we take a short break of 6 minutes, then we start at 15 past 11, right?